Welcome to Chapter 13, Waves and Vibration. So here we have a picture that will introduce some of our new language or characteristics that we'll use to describe waves and vibration. So here on our graph we have displacement, right? And so amplitude here, right, is the maximum displacement. And so we'll often, right, we'll actually call that A. So we can think of A as kind of like the maximum displacement. Time period, right, this is the time it takes to make a complete cycle, right? So this is the period, right, which we've been using as T. And then the frequency is how many cycles are within, right, a time period of 1 second, right? So if this was, right, from here, 1 cycle, 2 cycles, right, and this was 1 second, or yeah, so say this was, so it was 1 second is our time between then our frequency would be also 1, right? Because 1 second to complete 1 cycle, right? Frequency, right, is defined as the number of cycles per second, right? Which we are going to call hertz. And so that's another one of our new terms. So in this unit, we're going to talk about simple harmonic motion, and we'll start off by looking at a situation that we've looked at before back in chapters 4 and 5. Then we'll talk about equations of motion. That's familiar, but equations of motion here will be different because it'll be related to waves and vibrations. Then we'll talk about wave motion, wave properties, and then standing waves and resonance, where resonance is not resonance like in electronics, AC electronics. So here is a case where something very similar to things that we've looked at before, again in chapters 4 and 5. In chapter 5, we looked at the scenario of our moving box where it wasn't moving, right? Then this one happens to be stretched. We're stretching it, right? So we have our maximum amplitude, right? And then we release it. And back in chapter 5, we looked at this kind of scenario in terms of conservation of energy, right? Here we have no friction, right? That's dampening our harmonic motion, our simple harmonic motion. So here is our starting point. This is where our spring is neither stretched nor compressed, so we're in equilibrium. Then we stretch our spring, which is attached to our box. Here's our applied force. Here's the restoring force of our spring, right? Down here where K is the spring constant, meaning that it's constant unless we deform our spring, right? Deforming our spring is from chapter 9. And then here, this is our displacement. And again, right, we've seen these equations before in chapters 4 and chapters 5. Then, right, we have our maximum amplitude. We release this, and the restoring force of the spring makes our box then move back to equilibrium, but it still has energy, it's in motion, and then it continues to compress our spring, right, until it compresses the same amount as it was stretched initially, that maximum amplitude, maximum X. And then it starts to move back out, and so here we're back to where it was when it was in equilibrium before we stretched our spring. And then because energy is going to be conserved here, right, because we have no friction, it's going to come back to its starting point, in which case then it will start moving back to the left. Why? Because there's still this restoring force of our spring, and that's how we have this oscillation, right? So the mass on a spring without friction, right, then oscillates between its release point and the point that's equally far from equilibrium, right, which they've labeled as minus A. This is simple harmonic motion, right, where we have a pretty simple restoring force, just the restoring force of a spring. So let's kind of recap some of our new terms, variables. We have displacement, it's x. We've talked about displacement since chapter 1. Amplitude is the maximum displacement, so how much we stretched it initially, and then when we release it, right, it will go that same amount of amplitude, right, to the left of our equilibrium point, where they labeled it minus A. Our period is the time for one full cycle, just like chapter 7, and it'll be in seconds. And then frequency, just like chapter 7, is the number of cycles per second, or hertz, and frequency is 1 over the period. All stuff that we've seen before, the spring and the box moving, right? Most of these terms, except for the amplitude term, right, are from previous chapters. We're just going to look at them maybe in a way that's a little different. So when we talk about wave motion, we have to talk about the relationship between wave speed, right, which is our v in this equation, our wavelength, which is this funny lambda, it's a Greek letter, our period, which again is capital T, and our frequency. Because period and frequency are related, we just have two different ways of writing our velocity wave equation, which is, it could be the wavelength divided by the period, right? But 1 over the period is the frequency, so it could be the wavelength times the frequency. When you talk about light, right, we also talk about the same equation, that the velocity of light in a medium is equal to its wavelength times its frequency. Here, frequency is also set, right? Even if we have a wave that bounces off or enters a new medium, right? The frequency doesn't change. What changes is the wavelength and the wave speed. So here we have just kind of a visual to think about the difference between a high frequency wave and a low frequency wave. So our high frequency wave in the same time period, so remember this is time, right, here along this axis. So at the same time period, we have fewer cycles, right, with our red low frequency, right? So from here to here, right, that is, right, 1 period, right? And then from here to here, that's 1 period for our high frequency. Here, the period is shorter, but remember that frequency is 1 over, right, the period. And so they're inversely proportional. So if the time that it takes for 1 complete cycle, the period is small, then the frequency is high. And alternatively, if the time that it takes to complete 1 cycle, the period is larger, then the frequency is lower. And so we're going to flash to a nice little Phat simulation. So here I have created a standing wave, and I just happened to freeze it. Right? And it's fastened on this end, and I have no dampening. And I can change my frequency. It's pretty hideous. Right? I can change my amplitude. Make it larger. It's kind of crazy, right? Or I can change this to just a pulse, so we can just see what 1 pulse would look like. So here I have, right, my amplitude, right, and set, and here is very much like kind of the visual of our spring. Right? And so It just keeps going and going, and it won't stop because I don't have any dampening. If I have dampening, which is another nice way of saying friction, right, then I can come in here. Can't even make a cycle because I have so much dampening. I can also come in here and change my pulse width, make it smaller. Or I can change my pulse width, and make it bigger. Oh, now I got crazy stuff going on. Oh, forgot that I need to restart. Right, so I'm going to do a pulse, and I'm going to make this longer. So what does that mean? It means that it's slower. Right? Oh, I have a little bit of dampening. Let's get rid of the dampening. Now I could go in and change it to manual, right? So I can make it move. I can also replace my end. So I have a loose end. I'm going to do the pulse again because the pulse is fun. So I can have a loose end, and I can see what happens to my pulse. I have a really wide width, so let's see what happens then if I make my pulse width a little smaller. But what happens instead if I have no end and I just send a pulse? Right? There's no way for it to come back, right? So it just translates down my string, right, and then goes off into, right, oblivion, right? So here we can see a little bit about what happens with our amplitude, our pulse width, right, dampening, and then we can also play around with tension in our string. What does that look like if I change it to a loose end instead, where I have less tension? What about if I have even less tension in my string? So I can see how all of these variables, right, affect the wave of my, and then we can do the oscillate because it's just fun. So here's our frequency because it's an oscillation instead of a pulse. Oh yeah, I have really low tension. And now they're coming back and my waves are interfering with each other. And that's why, right, I have like this really crazy looking series of waves because, right, it reflected off the end and then, right, those actually interacted with each other. It's fun times. So we can look at waves and vibrations again by looking at something that's very familiar, and in this case it happens to be a pendulum, right? So vibration just means a movement to and fro, some kind of oscillation, and we know that a period is the time that it takes for one complete cycle or a complete oscillation. And so for a pendulum, the period is independent of the mass right? Whatever the mass is hanging off of our string, or a child on a swing, whatever our application happens to be. And so we pull our mass back at some angle theta relative to the y-axis, the vertical axis, and then we let go, and the period, right, ends up dependent on the length of my string, right, as well as the acceleration due to gravity. We could derive this, but we won't. So the period is equal to 2 pi times the square root of the length of our string, right, divided by g, where g is just acceleration due to gravity, right, just the magnitude, 9.80 meters per second squared. Nothing new there. That's nothing very different than what we've talked about before. So how about if we think about this in the context of a kid on a swing, right? So the kid is on a playground swing, swings back and forth, right? The ropes are 2 meters long, so that's L. And we want to know what is the period and then what is the frequency. So I can use this equation to calculate the period, right? So it's just going to be 2 pi times the square root of L, so 2 meters, divided by G, 9.80 meters per second squared. So from this, we can see that our meters cancel. We're going to end up with a period in seconds. That's always a good sign. So we'll take 2 divided by 9.8, and then we'll take the square root of that and multiply by 2 pi, and we get 2.8. So our period is equal to 2.84 extra seconds. Now we want to know the frequency. The frequency is just 1 over the period. So we can take the reciprocal, x to the minus 1, and we get 0.352, right, cycles per second, which is a hertz. And that's it. That's all we have to do. So the longer the rope of our bob, of our swing, the larger the period. Actually makes sense, right? We've all been on swings. So here we have another application of something that seems very familiar. How about if we look at something else that's familiar? Here we have a hanging spring. So we have a spring hanging. We've applied a weight, right? And we pull, the weight pulls our spring down. There's a restoring force again, right? So the restoring force of our spring is still x, or sorry, the spring constant times x. Here, the maximum amplitude is how much this spring, right, stretched, and then I let it go, and it's going to oscillate, right? And so there we have the motion of our bob on a spring, right? In chapters 4 and 5, right, when we looked at springs, they weren't oscillating, right? We talked about spring stretching in terms of forces. We talked about spring stretching and compressing in terms of energy. And now we're just not going to dampen it. We're just going to let go, and it's going to oscillate. And so this is another application of simple harmonic motion. So here's just another graph. And since our oscillation, whether we look here or here, looks an awful lot like a sine or cosine wave. And in fact it is. So we can see here, right, that we have an equation that describes our motion. And it happens to be, for this case, cosine. So y, being the displacement at any point in time, is equal to the maximum displacement, A, times the cosine of omega t. So if we remember back in chapter 7, omega, we called that the angular speed, it was 2 pi f, right? Which is the same as 2 pi divided by the period. and then we have t here, right? T because it's a function of time. We can tell that because as time progresses, right, y changes. Sometimes y is 0. Sometimes y is a. Sometimes y is minus a. Right? But we can calculate y at any point by using this representation of the motion of our oscillating spring. So here, right, in this scenario, it was cosine, right? And in this one, it's sine. So why is that? Well, it's because at time is equal to 0, y was equal to a. How can that happen? Well, the cosine, right, of, I'll call it 2 pi f t, would have to equal 1, right, in order for y to be plus a. If it was a sine, right, then at time equals 0, there's not a way for it to be, right, y equals plus a, unless I had a phase shift in there. But we're not going to talk about phase shifts. So in this equation, we say, you know what, it's a lot easier to say that really, in the end, we can look at this in terms of a sine wave, right? That would just mean that sine wave means that it starts off at time is equal to 0, y is 0. So sine, because at time is equal to 0, y is equal to 0. That's the difference, right? Opposed to time at 0, y is equal to plus a, meaning that it has to be cosine, because if the sine of 0, right, is 0, if we come over here, right, the cosine of 0 is 1. Right? So that's the difference here, right? So this is the cosine of 0 because time is equal to 0, and that's equal to 1. So that's how we can decide if it's cosine or sine. So here, right, we can look at our equation of motion, and then we can say, well, you know, if we have this hanging spring, we can think about our analysis of our period of the motion by using this relatively simple equation where the period is dependent on two things: the hanging mass and basically, right, the spring constant. So how stiff is the spring? The hanging mass is going to need to be in kilograms, and our spring constant is going to be in newtons per meter, just so we end up with the right units. And since frequency is 1 over the period, we can just rearrange it. Since omega is equal to 2 pi f, right, we just end up with the spring constant over the mass, right? They're just simple algebraic, right, rearrangements of the same thing. So here we have the displacement of an oscillator that's in simple harmonic motion, and they give us the equation. So here, right, y is equal to 0.25 meters times the cosine of 314 times time. Right? It doesn't say it, but this has to be in hertz or 1 over seconds in order for the stuff inside the cosine to be unitless. So what does this really mean? This means that this is equal to a. Right? So that's our amplitude. And then, right, if we come back over here, right, we have 2 pi ft. Right? This one happens to be cosine. Right? So this is 2 pi f times t. right? So that's how we know it's 1 over seconds, right? Because this is really 2 pi times the frequency. And here we just want to know if we look at our equation, right, at different times, what will y be? So in our first scenario, if t is equal to 0, right, then this is exactly like our first case with the hanging spring. So then y is equal to a times the cosine of 0. Cosine of 0 is equal to 1. So y is equal to a. Right? This is where we've stretched out our spring. At 5 seconds, right, now we have something that's a little more complicated, right? So we have, I'm just going to write it, it's a. And then we have cosine, right, of 314 times 5 seconds, right? I'm just going to have my units cancel. So in here, right, I have, whoops, 314 times 5. That's 1570. That's not degrees, right? That's 1570 radians. So here, because we have a function where we have 2 pi f t, right, really means that we have to think about our calculator in radian mode. So we have to go in and change that. So I have to go in, click mode, and then I'm going to come down and I'm going to select radian mode. Then I have to hope that I remember to change it back. And then I hit mode, oops, hit second and mode again so I can quit. And now I have the cosine of 1570, right, is 0.69933699993. Right? And so I have a times I'm just going to call it 0.70. So at this point, right, I'm at 70%, right, of my maximum A. So take 0.70 times 0.25, and y is equal to 0.17. And that's in meters. How about 15 seconds? So if I do that, right, then I have y is equal to a times cosine of 314 times 15. Oops, hold on. 314 times 15. That's 4,710. Now I'm going to take the cosine of that, again, in radian mode, and I get negative, so I have a times negative 0.73. So now I'm on the other end, right? So I'm down below the x-axis, which is time. And so I take that, I multiply it times 0.25, and I'm at negative, right, 0.18 meters. And so I can see how I'm changing with time. What if I wanted to know what the frequency was? Well, then here they gave me enough information to figure that out, because I know the format is really y is equal to a times the cosine of 2 pi f times t. So here 2 pi f is equal to 314. So then what's f? F is 314 divided by 2 pi. And so it's 50. So it's 50 hertz. Our period is 1 over that. So we'll take the reciprocal of 50. And so our period is 0.020 seconds. So at 5 seconds and 15 seconds, we've gone through many cycles. That's how these numbers in here are so large, right? And again, that's why we're also talking about, right, things in terms of radians opposed to degrees when we do these calculations for cosine. So if we look again at simple harmonic motion and focus in on the position, right, which we just did, right, then we can go a step further and calculate the velocity as a function of that position. And so here we have the velocity at any time is plus or minus the square root of these things. Plus or minus, just like back in chapter 2 and chapter 3, depends on where we are in our sine wave. So, or cosine wave. So if we started off with a cosine wave, right, we could have our velocity be positive. We could have our velocity, remember this is position versus time. Right, so we could have our velocity be positive, we could have it be negative, right? And so that's why plus or minus. Everything, we take the square root of this, it's never going to be inside here, it's never going to be negative. How do I know that? Because my spring constant is not negative, my mass is not negative, and x squared is never going to be bigger than a squared. Right? The biggest it can be, right, is when x squared is a, and that's where we change direction, right? That's where our velocity is equal to 0. Right, up here, again, velocity equal to 0. Right, we're changing direction, so it's exactly like those graphs that we looked at way back in chapter 2. When x is equal to 0, right here, x is equal to 0, whoops. When x is equal to 0, at that point, right, this term is 0, and we end up with V max is equal to the square root of k over m times that amplitude, right, the maximum displacement. So what if we're interested in the maximum speed? So here's another case like chapter 2 where we have to be careful about the words in our story problem. So we have a mass attached to a spring. The mass is 0.50 kilograms. And the spring constant is 10 newtons per meter. And our object is pulled down 0.050 meters from the equilibrium position. Translated, that's A, 0.050 meters. It's 5 centimeters, right? And then it's released, and so right, we're interested in our picture. Right, so we're looking at the maximum, the maximum velocity, which is when x is equal to 0, so that we end up with this simplified equation. And so to figure out V max, we just can plug our numbers in. So we have the square root of 10 newtons per meter, right, over m, 0.50 kilograms, right, square root of all that, and then we're going to multiply that by 0.050 meters, which is just A. So this is what was given. And so literally, we can go in now and just do our calculation. So we have 10 divided by 0.5. That's easy enough. That's 20. Take the square root. That's 4.47. And then multiply that by 0.05. And I end up with 0.224. I'm just going to call it 0.22. And I know that the units have to be meters per second because I used SI units. How do I know that? I could take apart the newtons. So Newton is a kilogram meter per second squared. And that's over kilograms. And so, and over meters. So this is over meters. And then over kilograms. So meters cancel, kilograms cancel. I have 1 over seconds squared, and then I'm taking the square root, so that's 1 over seconds, and then I'm multiplying by meters. So I end up with meters per second. And so it's always good to do that kind of unit check to make sure everything's all okay. So this is the maximum velocity. It's not always the velocity. Again, where it changes direction, that's where the velocity is equal to 0. Again, just like chapter 2. So here we have an equation of motion where we are looking at the velocity in terms of time. And we could look at the acceleration. Since our velocity is changing, we know our velocity is changing because my displacement versus time graph, right? My velocity, my slope is changing, so my velocity is changing. And so my velocity is based on time, and then my velocity is changing, which means that I have acceleration. But it's a constant acceleration. That's how here we, oh, sorry, it's not constant. Right? But here, right, we've just substituted in, sorry, y, right, for our a sine omega t. So this, right, is using a sine omega t. Right? Reminding you again, omega is just 2 pi f. 2 pi times the frequency. So now we can think of, right, chapter 5 and reflect on simple harmonic motion and potential energy. So if we're still talking about a spring, right, where x is the displacement, the change in the length of the spring, right, then we have the same potential energy of a spring that we had back in chapter 5. Right? The potential energy is 1/2 kx squared. Total mechanical energy is conserved here, right, because we don't have anything dampening our system, right? We know the amplitude, the maximum spring displacement, and so now we can calculate the total energy. So this is the total energy of our system, where we have our maximum spring displacement. Maximum displacement means that this is the total energy. Why? Because at that point, it's not moving. There's no kinetic energy. Right? Remember that the energy of our system is going to be potential plus kinetic. So at this point, it's not moving. This is the maximum displacement. So this is where it's about to change direction and swing back out the other way. So if we look at our spring on our surface that we looked at the very beginning of this chapter, then we can see how our kinetic energy changes with time, our potential energy changes with time, but how when we add them, we end up with a constant energy, right? Because here, well, energy is always conserved, but our mechanical energy is conserved. So here, in this case, right, mechanical energy is conserved. So we're not losing anything because of friction. If we dampen our harmonic motion, more like the real world, because we have some friction or air resistance or something, right, then we start off, right, with a certain amplitude, but that maximum amplitude, right, decays with time, right, and so we have what's called a dampened harmonic oscillation, which means that eventually it'll come to rest, right? That's the reality. There's no perpetual motion machine. We can't pull, right, our box down on our spring and then expect it to just bounce forever. Here is something similar to what we saw in our Phat simulation, where we give a little jerk to our rope and then we see a wave pulse that propagates down that string, and so that we see, right, energy transferring, right, without transferring matter, right? So the energy in the string makes us continuously see that disturbance travel down our string. Here we have a similar case again from what we saw in that Phat simulation, where we have a harmonic disturbance, right, where we set up a sinusoidal wave, right, and we have a wavelength, and we have velocity, and we have amplitude, right? This is exactly what we saw with that scenario. We can have wave properties change. For instance, our wave of some kind can enter water, right? And so that can change our speed as well as the wavelength, right? Right? And also the direction, right? And this is called refraction. We usually talk about refraction a lot more sometimes when we talk about sound, but certainly when we talk about light. Here's just a little bit of what we saw in our simulation with standing waves and resonance, right, where we have our waves going up and down, and we have time is equal to different multipliers of the period, right? So t is equal to the period divided by 8, for instance. When we have these kinds of standing waves, we talk about nodes, which is where it crosses 0, right? And we have antinodes, which is where the maximum displacement happens to occur. Here's just another simulation, right, where we start with one of our little pendulums moving, and then that movement gets propagated to our other pendulum, which is, right, down the string from the first one. And so we can see, right, this propagation of waves, just kind of a cool thing. Again, this is the same idea of standing waves and a rope, right? If we have a perfect, right, harmonic, right, where we have first harmonic, second harmonic, third harmonic, that means that our waves fit perfectly between our fixed ends. Right? And so that is when we have a resonant frequency. Right? We didn't always have a resonant frequency in our simulation because right, our frequency didn't match, right, so that we had a set number of complete cycles within our length of our rope. And that's the end of chapter 13.